So before lunch, we were trying to prove this, that the Riemann hypothesis implies the Lindelof hypothesis, and we will do this in a precise form. So log of the Riemann zeta function is, if it will be given by, will be bounded by log of this. This is a statement we already wrote down last just before lunch. I've just written it again. So yeah, so we started proving this. We said that the ingredients were Hadamard's three-circle theorem, and which for the moment you can take as a black box, and we will do it after we finish. We can do it as an exercise. It's quite easy. It's about log concavity of three-circle theorem. Or is it called a lemma? Maybe it's called a lemma. Do you know that a lemma is more important than a theorem? Because when a lemma gets known, it means it's really good. Whereas, I mean, so I mean, not all lemmas are more important than all theorems, but certain lemmas are so great because they are lemmas. So they are called lemmas. So, okay, so we started talking about this, and then we said, so how did we prove it? We said that for the proof, we were assuming, so let the Riemann hypothesis be true. All this we assumed in the morning. And then for large R, we considered the function. I'm just writing it, this definition again, because if I don't write it once, it will be difficult to prove it without S0 plus omega by zeta S0, and S0 is 2 plus I tau. The 2 here you can see from where it comes. Yeah. So so what is this? So this, we saw that this is holomorphic in the disk where this is smaller than something, and we said we could take it to be smaller than 3 by 2. Actually, what you know is that, so another ingredient is this is a bound for zeta S, and in fact, a bound like this is good enough. it is less than log of tau. Yeah. So, and when is this true? The absolute constant depends on sigma, and this is true when sigma is greater than half and tau is greater than 2. Could be equal as well. Okay. So, no, I said something wrong. Tau is less than log tau. No, that's fine. Sigma is greater than 1 minus constant times constant by log of tau, and this is true for all positive constants C. Yeah, this is true for all positive constants C. So we did this much, and then we had our FW, and what did we do from there? So so this from here, from this ingredient, from ingredient 2, this ingredient 2, we could show that, you remember we did this, the real part of FW is less than or equal to big O of log tau for omega less than something, which, as I told you, it's the 3/2, like 3/2 is a good result. It doesn't have to be 3/2, it could be something else that is good enough for us. Okay. So, yeah, so now comes this, the ingredient 3. Ingredient 3 is, I think I didn't tell you, did I tell you this morning? In that, did I talk about the Borel-Kara-Theodori lemma? No, which is also called the real part lemma. Okay, so this is a classical result. Okay, this is a classical result from complex analysis, and this says that if f of s is holomorphic for in some place s, which is less than or equal to r, it's just a number r, and f0 is 0. Okay, we let maximum of the real part of f of s, where this is actually attained, s is r. Well, maybe it should be written under this rather than here. Okay, real part of f of s. This is bounded. So if these conditions, so f of s is holomorphic, it's 0 at 0, and the maximum of the real parts is bounded, then we can show that the absolute value of fk of s, this is less than equal to 2 times a, this a, okay, the bound r is this r. The r here is this r here, and the a here is this a here. okay, the bound. The little k comes back here, factorial k. So r minus k plus 1, and this is true for all k positive, and it is also true that I already have. So for this is true for all k greater than 2. So this is my ingredient 3, which I'm going to use now. I don't need it in its full force, okay? But I stated the result in its complete form. In case we decide to do it as an exercise, we could. Nobody can stop us. So, yes. So then what do you have now? So you have that log of, where am I? Here. So real part of f of w is less than some log of tau. Yeah. So, right. So now from ingredient 3, which is this classical result from complex analysis, log of zeta s is log of tau, and sigma is greater than half, tau is greater than equal to 2. Okay. Now what I will do is I'll cleverly choose the parameters. Okay. Everything depends on that. So let S is equal to sigma plus IT, I tau, sigma plus I tau, sigma greater than half, tau greater than some tau 0. Yeah. So we will choose sigma 1, which is greater than 1 and which is less than equal to tau, and we will choose epsilon, which is of course positive, and which is the smaller of the two elements, sigma 1 minus 1 and sigma minus half. I suppose that this minus 1 and minus half is something that by now you've seen several times. Okay. And now we will use our ingredient 1. You didn't expect it to not use it if you had. So we will apply now I1, that is 3-circle lemma, to cleverly chosen points. Yeah. So we will use it to log of sigma 1 plus I tau plus omega, and then for 3 circles I need 3 points, right? So which are my 3 points that I'm going to choose? I am to choose R1, R2 and R, right? R1 is sigma 1 minus 1, and then you subtract epsilon from it. R2 is sigma 1 minus half minus epsilon, and R is equal to sigma 1 minus sigma. Now, do you understand why I am okay? So this one. So where is it? Here. So here you see you will have, what is your function here? You have, before that you had the real part of f of u is smaller than log of tau. Yeah. So now if you take the real part of this, then you come to this log, because f of w is log, is defined to be the log. Yeah, it's defined, it's by definition, it's constructed to be the logarithm of these two functions. So instead of writing it as f of w, you're simply writing it with its definition and taking the log. Okay? But as I said, you don't really need the full strength of this theorem. Okay, it's enough as a special case of this if we take, I mean, this is true for all k. Yeah. So here, if I take if I take k to be equal to even 1, this will do. Even 1, then I get absolute value of that, and I get log of zeta. I get log of zeta s from here. Yeah. Right. But you don't need an equality. What you need is an inequality. So it's you just need a big O. Yes. Yeah. It's from here, right? From here. This is the log. I think k is equal to 0. I don't think you even need first derivative. K is equal to 0 will do. Yeah, maybe I should not have stated this in such a big fancy way. I mean, for us, for this part, it would have been enough to have k equal to 0. And then you don't have to go to derivatives. Okay? So, so now I take these 3 points, R1, R2, and R, and do you realize what happens when I take these 3 points? These 3 points, it means that when I take my circle going through 3 points, which what happens to my, this is just a remark that I'm making. Yeah. So this is outside, I mean, it's a remark. The remark says that the point, so this is my point. I have sigma 1. Yeah. Here I have sigma 1 plus I tau plus omega. Yeah. This one, sigma 1 plus I tau plus omega. This one, it should pass through 3 points for me to use the Hadamard 3 circle theorem. So it passes through 3 points. So those 3 points over there, 1 plus omega plus I tau. Then secondly, it passes through S. And thirdly, it passes through half plus epsilon plus I tau. Okay, so this just to understand why we construct these 3 points. Okay, and then now I'm going to apply my ingredient 1, which is the 3-cycle lemma. Yeah. So log of okay, so log of zeta s by using the Hadamard's result, this is less than you have m1 which was the maximum, 1 minus alpha, and m2 to the power alpha for a certain alpha. So which alpha will do? So with alpha, I had the log results. So I use alpha to be the natural log of r by r1 and divided by r2 by r1, okay, which is equal to log of sigma 1 minus sigma 1 minus 1 minus epsilon, yeah, divided by log of the second point, sigma 1 minus half minus epsilon divided by sigma 1 minus 1 minus epsilon. This is my choice of alpha, and this is equal to 2 times. I can take out the main term from here, which is 1 minus sigma plus epsilon, and then I get a big O term, which I'll be able to forget, but I should write it out precisely. So this is sigma 1 minus 1 plus epsilon. Okay. And what remains then, so we have alpha. We still need M1, and we need so what is M1? So with alpha is equal to this, let M1 be, I choose M1 to be log of the supremum of the log of zeta. So you see here I have sigma plus I tau, yeah, and the supremum is taken for over all sigma which is greater than or equal to 1 plus epsilon, and this is less than 1. Yeah. And what about M2? M2 is less than log tau, and yeah, this will always be true. You can choose for a suitable choice of tau 1, choice of sigma 1. Yeah. For example, you can choose sigma 1 is 1 plus log of tau. And if you've done this, you've been able to construct alpha, M1, and an M2, and that's what you wanted to do. Therefore, you have shown that the result is true. Yeah. So, as an exercise, maybe we can start with something quite simple, and I suggest that we prove the 3-circle lemma. Yeah, that may be an easy thing to do. Let's start with the 3-circle lemma. I said that was an exercise. I stated the 3-circle lemma, I think, already, and said that, or should we do the, okay, let's not do the 3-circle lemma. Let's do something more interesting first. What I want to do that's more interesting is as an exercise. Show that the Riemann hypothesis implies the convergence of the series sum of mu of n to the power s, n equal to 1 to infinity, for all s in the half plane. S is excuse me, half plane, sigma greater than half. So what's interesting in this question? This is the Dirichlet series which is attached to which function? Which mu is this? It's the Mobius mu, just the old mu which we knew when we were children. Yeah, it's not the not the difficult kind of mu that Lindelof told us. This is just arithmetic mu n. So if you see a problem first, you should see whether the question is interesting. I mean, what could be interesting in this question? So convergence. So why do you think we are saying that the Riemann hypothesis is required to prove such a thing? It's a big thing. I mean, we don't pull out Riemann hypothesis from nowhere for no reason. Does mu of n yeah? Yeah, that's it. Because if you remember, this is 1 by zeta s, and there may be so if there is a, I mean, if the function were analytic, there wouldn't be any problem. But you don't have the analyticity. So you need that. And now I want to prove that the Riemann hypothesis is if the Riemann hypothesis is true, then this series converges for sigma greater than half. So I don't know how you want to proceed. Do you want to proceed with no hints at all, or do you want me to give you some hints? Do you want to proceed from 0, or should I be kind and take you along a bit? Should I be kind or cruel? What should I be? Okay, do you have any idea at all of what no, I'm sure you know. You know everything. Excuse me? Yeah? You already know how to do it? Have you already done this before? No. So no, that is where the problem is. So now how do we proceed? There is a psychological hint. This is not mathematical. If we've done something today, we probably are going to use it today. What have we shown? What is the theorem that we use today? We show the one theorem that we proved today. This is that the Riemann hypothesis uses the Lindelof hypothesis. So I suggest that you use that. Okay. So since the Riemann hypothesis is true, what happens? That is one thing, and that is the second hint. This is hint 2. Okay. And hint 1 is theorem 1. This is hint 2. Hint 1. Okay. Well, do you have ideas? Let's see if we have some ideas and if we can. Because first, as Shubhajit, your name is Shubhajit, no? Shubhajit said the problem was this had zeta in the denominator, so we have to get rid of that. Now, yeah. By the way, have you seen this theorem somewhere? Landau's theorem that if you have a Dirichlet series which is convergent somewhere, and if sigma 0 is a real number such that we can have an analytic continuation with, now here, which mu is this? This is the other mu. Yeah, I don't know. I think that they were quite bad in using their notations. I mean, you don't bring in two mu's into the same which f? Ah, the Dirichlet series. Anyway, when you see sigma, you see it's not n. Yeah, and in that case, you can your analytic continuation, you can continue further. This is what. Have you seen such a theorem ever in your life? I don't know how much complex analysis you have learned before, but did you see such a theorem? Okay, it's not absolutely clear to me that we should be doing all the complex analysis theorems here, because we are supposed to be doing arithmetic. So if these are tools for us, so yeah, maybe we can, you have 2 days. And so look up the proof. This is completely classical. There's nothing, I'm not asking you to make up some stories tonight. You'll find the proof. And it's true also. I mean, Landau proved it. So this was proved, I don't know, 1909 or something like that, really long ago. So there are tools which are they're not only classical, they're also classical tools which have been very well digested by now. It's not a 2024 result. Okay, these are old results. 1909 means now 115 years. We've been we are used to using all these results. So please study the proof yourself, okay? Or ask me if you really want me to do something. Okay, so now, do you see something here? I said this was a hint. Okay, so this thing is coming up here. Yeah, do you recognize this as coming from today's work? Yes? Yes. That's right. Yeah. No, it is not yet. Suppose no, it's not yet 1 by zeta s. You see, it will become 1 by zeta s if it is properly, if right now you can't talk about 1 by zeta s. If you just say summation, if the problem is given as mu n upon n to the power s, this is not 1 by zeta s yet. You have to make sure that yeah, the convergence. So it's this convergence which will make it 1 by zeta s. The guess was good. The guess was good that it should become 1 by zeta s. Is it? So don't go around in circles. So it's not yet 1 by zeta s. You show convergence and then it becomes 1 by zeta s. All right. So yeah, your argument is good. So how do we do this? So your first thing is hint. The first hint was that we were going to use the Lindelof hypothesis. Yeah, and we're going to use it, we can use it because the Riemann hypothesis is true. Okay, the Riemann hypothesis implies the Lindelof hypothesis. Yeah. So if the Riemann, so solution, okay. So so this one, let's call it M of S, M for Mobius. Okay. So where is this convergent? M of S is convergent where? For which sigma? For sigma greater than 1. Okay. And so solution, first of all, we assume that the Riemann hypothesis is true. Okay. So M of S is convergent for sigma greater than 1. And how far can I push it? How much can I bring it to the, so greater than 1 means I'm here. Yeah. Sigma 1 is greater than 1. Here it's okay. And as I told you, that one of the questions we always ask is how much further can we push it to, how much more can be included to continue analytically or meromorphically, or how far can I go from sigma 1 equal to 1? I can go till half. I can go till half. Yeah, sigma. So till here I can move. No problem. I mean, it is convergent for sigma greater than 1 and can be continued analytically to sigma greater than half. Okay. And because you can continue this to a sigma greater than half, now you can write this as you wanted to write it, as 1 by zeta s. Okay. So we take some function, let f of s, which I call it 1 by zeta s. Okay. You know here that you always assuming this. So if you assume the Riemann hypothesis to be true, then the Lindelof hypothesis is true. Okay. So since Riemann hypothesis implies the Lindelof hypothesis, theorem 1, therefore what can I say? You said something, somebody had an answer. Mu. So mu of sigma is 0. This is our crunch point. Okay. Mu of sigma is 0. Okay. And now you know, now we use Landau's theorem. And if I use it for sigma greater than half, then this is done. Yeah, because all the conditions are satisfied now. We have a finite abscissa of convergence, and we have mu sigma is 0 for sigma greater than sigma 0. So for if I take sigma 0, which is greater than sigma c, that's fine. Okay. So now apply Landau's theorem to get convergence. Okay. So the final solution looks quite simple, but behind it there are big things that have been done. Yeah. I like this application. So because it apparently looks I mean, you may not see the problem, but it requires very big tools. I mean, it really requires big tools. Otherwise, you cannot invert your zeta just like that. I feel like inverting it. Let's go and invert it. No. So a lot of work is required before that. Okay, now that this nice result has been shown, I'd like you to prove the three circle lemma. I don't know who proved it first. Maybe Littleboat did. So remember that, should I state the three circle lemma again? Does anybody have a question? So, I mean, it's not really clear. It's called Hadamard's three circle lemma, but it's not, I think it's not so clear if Hadamard really proved it. Hadamard proved lots of very big things, but whether he actually proved this lemma or not is not clear. Never mind, he was a great man. So, do you remember the statement? Hadamard's three circle theorem. We wrote it out in the morning, but let's write it again for just to make sure that we have the good notations. That was the first exercise, exercise 2. So that was exercise 1. That it's not, doesn't have to be exercise 1. It's exercise n, and then this is n plus 1, because we had some other things in the beginning which I had said you can try. So exercise 2. So here we go. So this is the three circle lemma. Proof the three circle lemma. So what was it? So statement is, you had a holomorphic function, let f of s be holomorphic on the annulus R1, which is, it's between R1 and R2, and some s, which is between these two. And let M of R be the maximum of f of s, and with s equal to r. You had a doubt about this. Somebody had a doubt about it this morning. Where's he? Ask him what his doubt was. So what is his name? He's your student? Ah, okay. So his question was, why should this exist? Okay. So MR is the maximum of this on the circle, and R is between R1 and R2. Yeah, but that's clear, right? R is between R1 and R2. Then M of R is log convex function of ln R in this area, R being between R1 and R2. Yeah, that's what we had to. So this is true for any three, any three concentric circles. Yeah. Okay. Okay. So who needs a hint for doing this problem? You need a hint. Who can do without a hint? If I say who needs a hint, everybody will ask for a hint. So who can do this without a hint? So yeah, of course, if you've seen the proof already, then you know the proof. So then just whether you remember or not is the question. You need a hint? You give me one and I see whether I can do with your hint. Give me a hint. Yeah. So what kind of thing are we trying to prove here? We are trying to prove log convexity. So so you're going to get some powers. Just think about something very classical from complex analysis. Yes. Who answered? You did. Did you study it already or you guessed it? Okay, so tell me. So everybody knows the maximum modulus principle. What does the maximum modulus principle say? Yeah, can you tell me? What is the statement exactly? What exactly is the statement? One thing is, I mean, people should have completely correct statements. No, not in a class, but in general, I mean, the completely correct. So that a maximum is attained on the boundary is true for whom? Well, which kind of, when is it? No, so it's true for a non-constant function. If you actually get if you reach the maximum within the domain, that means your function is constant. So it's an important point. Don't forget that. So you better construct a function that is non-constant. Yeah. So so that's the point here. Okay. This is going to be. This is what's going to. This is what's going to. So take R to be. I think R should not be equal to R1 and R2. Yeah. I think I have to remove the equality condition from there. What do you think? I think. Yeah, I think I should remove the equality condition. Yes, I should remove the equality condition, because otherwise, you see, when I get log R2 by R1, etc., I'm going to get all sorts of log 1s, and then let's drop it. Okay. So let's use the principle of so now you know this theorem. Okay, exercises that prove this. Okay, prove it on Saturday, and then for Sunday you can have another thing to prove. Okay, so it's time, right? So let us then try to finish this. So since R is between R1 and R2. So your guess was correct. We apply the maximum. Yes, now that apply the maximum modulus principle. But my question is, Adama, you know him, yeah? Adama, he proved the prime number. He's one of the people who proved the prime number theorem together with de la Vallée-Poussin. So, so apply the maximum modulus principle, but to whom do you want to use on what do you want to use your maximum modulus principle? So you should use it somewhere, yeah? Where do you want to use it? To which kind of function do you want to use it? You want your logarithm, you want the log convexity. So you will need some powers, yeah? So you take S power n and Fs power n, okay? And then what will you get? Then you will get that if you take R1 and R2, so R1 power m R1, here's my maximum, take it to the power n, R minus R1, you on the annulus, plus R2 to the power m R2 to the power n, R2 minus R. So this is going to be greater than or equal to R power m R power n. Now what you do is, you choose your m and n. So somewhere this might become equal. So let alpha, call it alpha, be such that there is an equality, and then so such that R1 power alpha MR1 is equal to R2 to the power alpha MR2. Okay. And now let this m by n become large. Yeah. Let it go to infinity. Then R alpha MR will be equal to R1 alpha MR will be equal to R2 alpha M R2. Okay. So this, now take the logarithm. You take the logarithms, and what happens? Log of MR, this is less than or equal to, so take the log here, log of MR, this is less than equal to log of R2 by R divided by log of R2 by R1. Okay? Do you see the idea of the proof now? Times log here MR1 plus, because it's now in logarithms, so I convert my product to sum, log of R2 by R1 divided by, should be R by R1, and that's what we had to prove. Yeah. So this is what we call log convex. Yeah, the log convexity has been proved. Next time you have to work harder. I'm not going to do all the problems. Okay. I'll try to give you some problems beforehand so that you can think about it, and that'll be easier if we think of it before. It's not so easy to just come like that and try to find the solutions. Yeah. Even if you work a bit, you have some ideas, and then we can finish it together.